Okay, so I'm back with the third part and the last part of this week 10 lab. And I'll bring up the lab here. Let's see, that's here. And so we're on the B part of section 2. And notice the circuit is the same. I'm just going to change the power supply. And in this case, because we've got this, this wonderful Pico device, one of the choices we had, first we just set it to 2 volts peak at a sine wave up here, but one of the other choices we have is a DC. And since 1.4 is less than 2, I should be able to set that. Everything else in the circuit is the same, and the measurement should be pretty straightforward and easy. So give me a second to readjust the camera, and we'll get right back. Okay, so I can better see the multimeter, and here's the thing, I'll bring up our oscilloscope, and this is where we left it with 2 volts. Actually, it was a touch under 2 volts here, right, because of that little bit of resistance inside the source. So what I'm going to do, let me put this here so you can see it real clearly. I'm going to change the source. Notice one of my choices here, lots of choices. Down at the bottom is I can make it a DC source. And right now it just goes flat like DC would. And the setting is for 0 volts. So I want to set that. I mean, I can run it up slowly, millivolts at a time or a bunch. But actually, you can go right in here and type in 1.414, which is what we wanted. And, you know, it should do that. And there it jumps up to 1.414. So if we actually took the scale down, see, you'd see it's 1.2. That would be, you know, 1 point in between those would be almost 1.4. So it's right about in between there, 1.2. 1.3, 4, 5, and then 1.6. So that's right where it is at 1.414. So that's now the value being put into our simple circuit. So all I did was change this. Change the type and the size. Easy to do in this circuit. And so why don't I just take a moment then, and we'll check some of these. So I don't want to get caught in this. Bob, you fool, you didn't change the red thing, so let's move that there. And I'm going to check voltage. And remember, I got to set this, so it wants DC, so there's DC. So I'm just going to look as a test for the DC voltage. And I got 1.417, so really pretty good. Okay? So it's probably set a touch high, because it's on the circuit, and so we just now measured this, and it turns out we got that. Okay, so we're going to measure all these again. You can calculate, and notice I don't have you fill out a chart. You just calculate the current once, and that's going to be Ohm's law. But just remember to use 1.414 and the total resistance. And then you can calculate the power in each resistor. So that's this, and you're going to take that and have that measurement, but then here you're going to use the measurement. So the resistance, you can copy the values from before. We measured those already, the real values. And you're measuring current and voltage. And then you'll calculate power as the product of these two. Okay, so I'm just going to measure some voltages, and we're on DC, and our meter still shows us at DC. So I'll check voltages. So here's our first one across the 2.2. What am I getting? Did I select this right? Okay, so let's check these things now carefully. I had the circuit a little bit open, so from the last measurements. So here's what's coming in, 1.346, right, instead of this. So it's a little bit downgraded because of that internal resistance in the supply. All right, now I'll measure the voltage across the 2.2K. And what's happening with it? Make sure the meter stays on DC. 251 millivolts, right? So 251 millivolts, I could write it as 0.251. Oh boy, scale's all wrong here and everything. Anyway, so that's 0.251 volts. You'll have to write that in and capture it. I'm going to be sending the new chart anyway. So you can just write these down by hand, or look at the video again when you get the new thing. 253 or 254 millivolts. So that's like a quarter of a volt. Now on the next resistor, the 3.9K, we get 0.447 volts, right? And what happens is the meter automatically adjusts between volts and millivolts. You know, and I don't know where the balance point is there, but those are the numbers. And then the last piece is the part on the 5K, and that's 0.645 volts. So that's about 0.6 of a volt there, and 0.4 of a volt there. So if you add those up, that's about 1 volt, a little over 1 volt, maybe 1.1. And then if I take the last little bit here, I add 0.25 or so. I'm going to get these to add up to, I'm talking about these values, they're all going to add up to about what they should be, right? This apparently is going to give me, I have the wrong text size there. Yeah, all too small. So that's another thing I'll get adjusted with these fillables. Okay, so we measured the voltages, and when you fill out the lab, you can just read them off the meter yourself. And the last thing then I need to do is measure the current. And I'll move this over to milliamps. And now I leave it on DC. That apparently is where it starts up. So I'll move my thing. So I open the circuit to measure current, and oops, once again, I'm a slow learner on moving these things. I think we mostly hate them because they're so hard to move. I can imagine in the field someone would have one of these for voltages and one of them for current, and that would be, of course, I put it in the wrong one. I put it in amps, and they'd leave them set up that way. Okay, so the amps looks like 0.1 something milliamps. Well, we know we're going to have to go down lower than that. And we're looking at, 113.9 milliamps. Oh, that sounds vaguely familiar. Let me see if I can write that in here, or if this is messed up too. Yeah, that's messed up too. So this is 113.9 milliamps right there. And that's going to be fairly similar to what we saw with the AC. Okay, in other words, this value up here, look, we had 113.6 microamps. And I'm sorry, we have, this is microamps. We have 113 point something microamps. Now isn't that 113.6 microamps again? So what happened here? Look, a series circuit. The current is the same in all elements. Here I put the RMS, the peak value in, but I measured RMS values. Here I applied an RMS voltage, and I measured an RMS values, and surprise, surprise, this current with a DC source turned out to be identical to this current with an AC source when I measure RMS. And that's the key thing of what's going on. With AC and DC become the same thing when you consider RMS values. Okay, so when the meter automatically measures RMS with AC, it's kind of giving you a heads up or a clue as to what the DC values would be. And the importance of that is that's the amount of punch, that's the amount of power, that's the amount of real capability of delivering energy. So we transmit voltage to houses, industry, and all that as AC. And what we do is crank up the peak voltage to the point where when the user needs to know the real power, if they treat it as RMS values instead of peak values, it's the same as plugging in a battery or a DC voltage of that level. You think about it a little bit with these two circuits, and you'll get the idea. These measured voltages here are going to be very similar to these. Oh, by the way, look, there they are. 1/4 of a volt, 4/10 of a volt, 6/10 of a volt, right? This is like 637 millivolts, 441 millivolts, 250 millivolts. Work those numbers around in your head when you plug them in and fill out the charts, and think about it as you send it in. And I'll quit with this, and we are done with Lab 10. And in our Wednesday call, our Wednesday Zoom call, this coming Wednesday, we can talk about this and go over it a little bit, and we'll move ahead if we need to AC to DC. How do we get DC out of AC at higher levels? We don't just have a simple voltage supply like this where we change the shape of the waveform here. It's a little more interesting than that, and we bring back diodes to make that happen. So I'll see you on Wednesday night, and I'll start producing more videos for the Week 11 lab. Thanks, and be sure to email me or set up a conference with me if you have questions. That's no problem.